Alright, this is going to be the lecture video for Chapter 7, Work and Kinetic Energy. So we'll talk about the work done by a constant force on an object, kinetic energy in the work energy theorem, work done by a variable force, and then power. So the basic definition of work is when a force displaces an object. So that means the force applied to the object has to be parallel to the displacement. AKA, if your displacement is horizontal, your force is also horizontal. You can say that work is equal to the force applied times the displacement. And we measure work in joules, or just capital J. Here are some typical values for work. So heartbeat is 0.5 joules, all the way up to the annual US energy use, 8 times 10 to the 19 joules. Lots of energy. When you have forces that are at angles, you can also have work. You just have to take into consideration that angle. So because cosine is our function for horizontal forces, you would just do the overall force, right, your hypotenuse of your triangle, times cosine of the angle, times the displacement of the object. So it's still similar, you just have to take into account that trig function to help you figure out the work done at an angle. You can also write it as the dot product between the force and displacement. It basically says the same thing. Sometimes for my kids this is easier to understand. So just the force times the displacement times cosine of the angle. So work done on an object can be classified as positive, 0, or negative, depending on the angle between the force and the displacement. So in picture A, you have positive work being done, as long as your angle is less than 90 degrees. If your force and displacement are more than 90 degrees, you don't have work being done because your force is not parallel to your displacement now. So this doesn't make sense. It cannot work, literally. If your force is more than 90 degrees, but less than 270, so not enough to make another right angle, then you have negative work being done. It just goes in the opposite direction. If you have more than one force acting on an object, then you can find the work done by each of the forces. So you can find the work done by the force of gravity as one work. The force of gravity times displacement. So you can say the work done by gravity. You can say the work done by the normal force. Etc., etc. Then you can add them all together to figure out the total work done, or the net work done. When you have positive work being done, you say that the speed is increasing, right? You have a force pushing in the same direction as displacement, you're going to increase your speed. Negative work means you're slowing down. Your force is opposite of your displacement. It's like you're pulling back and causing your object to slow down. We have a theorem for this. It's called the work energy theorem, or sometimes it's called the work kinetic energy theorem, because you can use the total work done by subtracting the final kinetic energy, which is this equation here, minus the initial kinetic energy. So you can also say that the work done is equal to the change in kinetic energy. So kinetic energy is 1/2 times the mass of the object times the velocity squared. Right, so again, we can say it's also the change in its kinetic energy. This is just written out again for you. If you have a nice constant force, if you graph position and force, position being on the x-axis, force being on the y-axis, if you calculate the area under the line, you can get the work done. So any force distance graph, if you calculate the area, you can find the work done. If your force is constant, it's a nice straight line, and the area is pretty easy to find. Things start to change when your force changes, becomes variable. But it's still the same process. You still take the area under the line for each force and just add them together to find the total work done. You can approximate a continuously varying force, so think like an exponential line, by doing the areas of succession by constant values like right next to each other. So for springs, right, we talked about Hooke's law in the last chapter. We know that it's the spring force equal to the constant times the displacement of the spring. So in this case, you can say the work done is 1/2 kx squared. All right, this is also the equation for elastic potential energy, which we'll talk about in the next chapter. But this is kind of that preview of that. So because your position is changing, the force is changing, right? Every time your distance goes up, your force goes up, you have this nice constant line on the graph, which if you take the area underneath becomes a triangle, and we know triangle area is base times height divided by 2. We can kind of manipulate that to our advantage for the work done. So this equation stems from the area of a triangle. So if you have your position of x down here, that's the base, times kx, which is the y. You multiply these together, you get kx squared over 2, right? Or 1/2 kx squared. Both mean the same thing. All right, and lastly, we talk about power. Power is the rate at which work is done. How fast is it getting done? So the most common equation for power is work divided by time. We also know that work is equal to force times distance. So you can also say force times distance over time. If it's done at an angle, right, you just put your cosine in there. Right, all these mean power. You measure power in watts, big W. So just be careful, your units for power is big W. Work sometimes is also represented as big W, so just make sure you keep the two separate. Oh, and then to compare to what we know for power, right, like horsepower in a car, is roughly 746 watts, just as a frame of reference for you. Here are some examples of power of different objects or places. You know, your home stove is about 1.2 times 10 to the 4th watts. Television's about 200 watts, etc., etc. So if your object's moving at constant speed, you can use the force to help you figure out the power. So force times distance over time, like we talked about. This also, right, distance over time or displacement over time is equal to velocity. So yet another equation for power is equal to the force times the velocity of the object. So there's different ways you can find power. Just depends on what information is given to you.